AMD Zen 5 CPUs will be launched on July 31st. So this is a dedicated news segment with some architectural information, a differences in comparison section on the chipsets. That's X870E, X870, B850, B840 against the prior chipsets. We covered that during the Computex announcement, but now we have some more info. So that's what we're going over here today. AMD's new features include on-the-fly memory tuning, some memory changes from within Windows being supported without reboot now, so that's kind of cool. There's a new curve shaper. We talked about that in our video from a couple days ago with Bill and Amit going over the overclocking. So you can learn about Curve Shaper in that one. That builds on top of Curve Optimizer. There's the new chipsets, there's the Zen 5 architecture itself, and we'll cover the rest of the news for AMD Zen 5 lineup as we know it right now. So all of this comes from a press conference that AMD held in Los Angeles. As always, we paid for all of our own flights, travel, hotel, housing, staff, obviously, things like that. So we flew out there on our own dollar. Thank you for the support enabling us to do that, and collected all this information. We put it together for you, and then the reviews are coming up closer to that July 31st date. But for now, at least we can get into some of the architectural differences and some of the expectations for performance that AMD has set with its first-party benchmark. So let's get into it. Before that, this video is brought to you by Thermalright and the Frozen Prism 360 liquid cooler. Thermalright's Frozen Prism is one of the most affordable liquid coolers on the market and is able to achieve competitive results with a high cold plate convexity that applies pressure centrally to the silicon area based on our testing. This works on both AMD and Intel. We previously benchmarked the Frozen Prism and found that it's overall competitive for its price point. The cooler comes in a few color variations. It has a blackout option and an RGB option, and it's the cheapest liquid cooler we've tested anytime recently that still hits performance markers. Learn more at the link in the description below. So we'll get right into the quick facts first. Some of this was already covered at AMD's Computex announcement, but a lot of it's new information. Unfortunately, the first thing everyone wants is price. We don't have that yet. That'll be closer to the July 31st date. Now, AMD's Ryzen 9000 series desktop CPUs are codenamed Granite Ridge, and these feature the Zen 5 architecture. They are still in the AM5 socket, so the motherboards can be the same, and then they are launching soon. Now, the first image will be a recap of things we already knew. So that's the core specs of the CPUs that are currently known. Then that'll be followed by the new information. So to recap it for you all, this shows the lineup is fundamentally identical to the initial Ryzen 7000 series CPUs. The flagship R9 9950X, which was the one we overclocked, or rather watched Bill overclock in the recent video, has 16 cores. It advertises a 5.7 gigahertz max boost, 80 megabytes of cache, 170 watt TDP. Down from that is the R9 9900X, with 12 cores, slightly lower boost and cache, and a 120 watt TDP. Then there's the 9700X that has 8 cores, it's got a 5.5 gigahertz max boost, a smaller 40 megabytes of cache, and that is due to it being a single CCD, and then it has a 65 watt TDP. And finally, there's the 6-core 9600X, which holds up the bottom of the stack. Notably, the TDPs for the bottom three are down versus their prior Ryzen 7000 counterparts. As a reminder, TDP doesn't equate the actual power consumption. It's not always consistent across the same companies. We asked about that, get to that in a second. And it is definitely not consistent across vendors or even across sockets. AMD's PPT, or package power tracking, would be the more reliable guidepost for sort of power comparison numbers. So the TDP formula is TDP equals Tcase minus T ambient divided by heatsink fan theta Ca, I think is what it is. So that is important that all those things are the same for the comparison to be like to like. We asked AMD, yes, they are all the same metrics. So the numbers that go into that formula for Ryzen 7000 and Ryzen 9000 should be like for like comparable. In other words, meaning heatsink fan theta Ca thermal resistance is the same. That's the key number. That one particularly mattered. AMD advertised that for Zen 5, it has improved the thermal resistance, they say, by 15% improvement in the Zen 5 solution for what they say is a 7-degree reduction at equivalent TDP. So we asked AMD's people, what exactly does that mean? What was tuned? How did it improve? And the answer we got was the tuning was largely to sensor placement and optimization of how the temperature is being read. There have been some other improvements as well as a result of the architectural changes, maybe some voltage stuff, but ultimately it comes down to sensor placement. So in any given CPU, there are multiple thermal sensors. AMD Zen CPUs have hundreds of sensors for different things across the chips, and changing the placement of them means that strictly like for like, it's not identical, but what they're trying to do is improve the boosting headroom by getting sensors out of areas where it may be leading to an unoptimized temperature reading that is, for example, jumping in to gate the boosting or thermally limit, maybe more accurate to say, the boosting earlier in the pipeline. So they're trying to get away from that. So that means the T-die performance should look better at least and may allow better boosting. All right, getting into the architecture stuff. So AMD gave the press a deeper dive into the changes for Zen 5. It's stating that Zen 5 it's sort of seeing it as a place to grow from for Zen 6 and Zen 7. Here's the beginning of that presentation.
And what you're going to see is it really represents a huge leap forward. And in fact, it's going to be a pedestal that we're going to build upon the next several generations of Zen.
On this presentation, AMD said that it redesigned key elements of the front end, including fetch, decode, and dispatch. This gives more instructions to the back end every clock tick. Zen 5 has wider execution pipelines to execute the instructions. AMD says that efficiency increases from improved cache with more bandwidth and an expanded execution window, which the company states is intended to avoid execution stalls. Moving into more detail and starting on the front end with pipe fetch, branch prediction is lower latency, more accurate, and with more predictions per cycle in Zen 5, according to AMD. This all adds up to more throughput in the front end. Downstream, Zen 5 has dual-ported instruction cache and op cache while decreasing the latency. AMD also added a dual decode path. Next is dispatch and the execution engine. Zen 5 features 8-wide dispatch and retire, 6 ALUs with 3 multiplies, and a more unified ALU scheduler. There used to be a unique scheduler for each of the ALUs.
We then went, from the fact that we had these wider execution pipelines, knowing that when you have more instructions that you're handling, you have to think about handling misses effectively and keeping the performance of those execution pipelines. Again, hardcore microarchitecture engineering.
AMD also expanded Zen 5's execution window by, it says, 40% with up to 448 supported ops, which AMD says is a significant driver of more performance. Zen 5 also has a larger 48 kilobytes data cache, up from 32 kilobytes on Zen 4, and double the maximum bandwidth to the L1 cache and floating point unit, and improved data prefetching.
When you grow caches like that, what typically happens is you run a high risk of increasing the latency. You grew the cache. That's normally going to happen. But what we did in this case, the team just did a phenomenal job. And so they maintained actually that 4-cycle access that we had, despite the growth, the 50% growth in the data cache. With Zen 5, we can now execute 4 loads per cycle.
The final key improvement AMD made regarding data bandwidth is to data prefetching, where AMD says the tuned algorithms give more stride pattern recognition. Next are the floating point and vector math unit enhancements. These include a full 512-bit data path, 6 pipelines with 2-cycle latency floating add, and a larger number of floating point instructions in flight at one time.
So I talked about that 512-bit data path. This is more important than ever because when you think about it, there's been no reduction in the kind of math-hungry workloads of gaming, of HPC, of content creation. So when you think about those users of the math unit, none of them are going away. But AI, with its needs, is now becoming a workload everywhere.
AMD so far has done AVX512 by double pumping a 256-bit pipeline, which made sure that the CPU wouldn't have to drop clocks while doing AVX512 workloads. With Zen 5, AMD engineered a way to support full frequency while running the physical data path at true 512-bit. Our understanding is that this is modular to the extent that the older double pump approach is still possible in some situations if they want to build it that way. Zen 5, they say, also lowers the latency of floating point operations from 3 cycles to 2.
So we doubled the physical pipeline, we lowered the latency, we've increased the throughput, and that combined with the load store improvements that I described really create a super optimized engine across those workloads I described. AI, HPC, gaming, content creation.
All these improvements bundled together result in what AMD claims as a 16% average geo-mean uplift in IPC versus Zen 4, with up to 35%, they say, for single-core uplift in AES XTS encryption. The breakdown of Zen 5's uplift consists of data bandwidth, fetch and branch prediction, execution, retire, and decode and op cache improvements. In a more physical sense, Zen 5 moves to 4 nanometer and 3 nanometer process technology. This should enhance, they say, the metal stack for higher performance and lower resistance. There's a change there as well. AMD also shared some first-party performance claims, so as always, we'll go over a couple of these just to set the expectation and know what we're benchmarking against in terms of validated marketing, but we're not going to go through all of them. It is first-party. The numbers should therefore not be looked at as full truth, and just view this as a way to set the expectations. We'll have our own review for launch. Okay, so the first set of tests were performed with matched clocks. AMD says between a 9950X and 7700X. Claimed IPC uplift ranged from up to 10% in Far Cry 6 to 23% in Blender. Geekbench 5.4 was even higher, though that seems like a potential outlier. We would have preferred if these were done with CPUs that were more comparable, so at least the same CCDs, if not the same actual core count. They lock the clock, so that helps, but AMD is basically asking us to give the benefit of the doubt that there is no advantage from a physical hardware difference between them beyond the architecture. So anyway, AMD's had some shoddy history recently with some of its marketing slides, like the Zen refresh stuff that they showed at Computex, where they chose a lower-end GPU to do a CPU benchmark comparison. Didn't really make any sense. But anyway, moving on to AMD's competitive testing, it matched up the 12-core 9900X versus Intel's 14900K. AMD claims a 41% improvement or advantage in Handbrake, 22% in Horizon Zero Dawn, and 4% in Borderlands 3. AMD also compared its 9700X to the 14700K, citing a 19% advantage in Puget's Photoshop benchmark. That's one we run in our review, so we'll check that. And game benchmarks that range between 4% and 31% in the 9700X's favor. Then finally, moving to the 9600X, AMD matched it against the 14600K. There's a massive 94% win in Handbrake, along with a group of other productivity and gaming wins. Now, interestingly, AMD compared to its former AM4 king, the 5800X 3D. AMD's probably having some trouble getting people to migrate off that platform with how good that CPU was. AMD ran the 9700X versus the 58X 3D, where it claims an average 12% faster geomean. That would be a huge efficiency win as well in theory, but we'll need to test it, look at the power draw, at the performance. At the end of the Architecture Day discussion, AMD had 4 of its fellows, they're called, on stage. If you're not aware, fellow is a common title in the industry. It's reserved generally for very high-ranking either engineer or management track people at companies. In this instance, this was the design and engineering team. So the 4 engineers included Mike Clark, who's the chief architect. We actually have a separate interview with him coming up soon. He is regarded as, they call him, quote, the father of Zen. He has another nickname as well that we'll talk about in that interview. And he is effectively the originator. Will Harris is a platform engineer. He knows the chipset and the socket. Mahesh Subramani is a silicon design engineer. And then Joe Macri is the computing and graphics CTO. It was a generally technical, if a bit top-level discussion at times. One of the early questions had to do with the fact that AMD is rolling out a heterogeneous core in some of its products. And so this was a SoC discussion, a lot of this stuff. But there was a funny slip, or maybe not, in this section. Let's see if you catch it.
Mahesh, when we look at our competition, Intel, they have a performance core, an economy core.
Definitely some stifled laughs in the audience for that one. I looked at Vitalii and I was like, did he say economy?
An economy core.
That's interesting. Anyway, Intel calls it the efficient core, but economy has kind of a different meaning behind it. Now, here's another quote from AMD.
We have heterogeneous cores also. Our philosophy is different in how we approached desktop or mobile. Maybe you could dive in a little bit there and explain why 2 companies that are aiming at the same markets approach things just so differently.
It really is microarchitecture exact, ISA exact, and IPC exact modulo the cache size it attaches to. So the heterogeneity, if you will, is really around the voltage frequency response. So giving up some of that peak frequency, peak performance, and get some of that back in area and efficiency. So that's what the compact core does for us. The desktop user demands performance, low latency, and throughput for every task they want to do. So they are better served with a homogeneous, classic core with a better performance, if you will, on a voltage frequency response, if you will, dynamic. And on the mobile side, even though they're not that far behind in their compute requirements, they care a lot about power efficiency, and that's where the compact core kind of fits right in. A right mix of the classic and the compact cores delivers that scalability in performance without compromising on the power efficiency.
AMD's Macri added that since AMD's compact cores are in essence the same as its regular cores, it makes things easier from an OS or a software and scheduling perspective.
The corner cases that you experience when you got cores that are very separate in their attributes just confound the user, make that user experience more difficult, make the OS partners have a more difficult life.
In some ways, interesting words from the company that shipped the 7950 X3D and the 7900 X3D, where these are CPUs with different performance characteristics that have CCDs where they've got one with stacked V-cache and lower frequency, the other one without the cache, but higher frequency. There are some scheduling challenges there, and those CPUs opened up a whole can of worms that in order to get the best performance in all circumstances, they do require special drivers and even a little bit of user knowledge and intervention at setup that we would classify as confounding. So interesting choice of words. They are not completely free from having some of the same considerations for users. The big thing is as long as it's all communicated well, so it matters most. And then, of course, on the OS side, all the scheduling does need to be taken care of. Intel has struggled with that, so fair point to AMD. It's just they have also had some of those struggles in the past. All right, moving on. Macri addressed Will Harris and brought up the AM5 platform, socket longevity, and said that AMD intends for AM5 to last up to 7 years, and they said 4 generations of CPU cores. AMD later emailed us and said they did not intend to say 4 generations. They intended to instead just give the year marker, and that was it. So we don't know exactly what that means, but it was a misspeak in some capacity. We'll see how that shakes out in a few years, I guess. Harris responded saying this.
And so one of the first things that we do as we're designing a new infrastructure such as AM4, AM5 is we kind of tie it to a major interface that's transitioning. So in general, it's usually memory, for example. So AM4 was tied with DDR4 and AM5 was tied with DDR5. Like you said, we want that longevity, so then we do things like making sure that we have sufficient interfaces to go for several generations. We make sure that we've got the signal integrity, isolation on the pins on the package, so that we can get a few speed bumps and improvement over time on things like memory speeds or PCI Express speeds, for example.
Harris also said that AMD evaluates industry trends, standards committees, third-party vendors to see where the market's heading long-term. I asked Will Harris a little later in the event about socket longevity and the types of trade-offs that might be made for something that is longer lasting. And one of the key areas that Harris brought up, actually a couple of them, were one, trying to align with technologies like the most recent DDR generation, so 5 in this case, aligning for PCIe generations to try and catch those as they're new because they're going to be supported for a long life, and making sure the pin count is appropriate so that AMD is able to work with all the pins it might want for such a long lifespan. Other downsides would be if they want to do a massive change of any kind, they're kind of restricted to the socket and the chipsets they've created and need to stick with it. So anyway, Mahesh from AMD jumped in and said that the generational gains in the same die area, with them slowing down, AMD has had to add die size in order to get more substantial gains in IPC and total performance. So if the dies get larger, they still need to fit on the same physical package, and that's a difficult challenge across multiple generations.
The team has to dive in at the device physics level, right? The process technology, as we shrink it, voltages want to come down, but the platform has to stay consistent.
And as AMD does, they did take the opportunity to get in another shot at Intel.
You don't have to go change your motherboard every other generation like some other folks do.
Fair enough on that one. AMD has done well. AM4 definitely has earned its legendary status for how long it's been relevant in getting new CPUs. So as long as AMD doesn't start doing the same thing as Intel at some point, then that's a fair comment. But we will remember that. So if that ever changes, AMD, I'm going to dig this up, even if it's in 10 years from now. I'm going to play it back and be like, hey, remember that time? Just some encouragement to keep doing the right thing. The conversation turned towards simultaneous multi-threading, or SMT, addressing Intel leaving behind hyper-threading on the upcoming P-cores in Lunar Lake.
I think as we talked about heterogeneity earlier, with Intel having two core types, one with SMT and one without, I can definitely see how that would be really hard to manage for software. So I can't really comment more on their design choices, but that seems like an obvious one that sticks out.
Now again, AMD 7950X3D is staring us right in the face with some similar scheduling challenges, but Clark continued addressing the actual topic at hand.
For us, I mean, SMT is what is the best per watt per area feature that we have. And implementation does matter too, so you have to do it in a very smart way, just like all the microarchitectural features, Mark rolled out yesterday. And so for us, SMT is about a 5 to 10% area hit versus, workload improvements that go from 20 to 50%.
Clark stated that SMT doesn't work in every scenario, and that if a workload is bandwidth intensive, having more cores won't help more than having SMT. AMD makes some processors with SMT off, and it allows the end user to, of course, turn it off. They also briefly discussed the future Zen 6 and 7 CPUs, but it was very limited, mostly to the fact that AMD is making them. And they also talked about how they view Zen 5 as sort of the launching point in a similar way to Zen 1. So it's almost like a reset for the platform for the architectures to come in 6 and 7. For the chipset comparison and differences, we'll keep this as simple as possible because there's going to be a lot of motherboards out there you can choose from as these generations pile up. So this will give you some tables to show the differences. There are going to be 4 new chipsets in the immediate future. There's X870E, that's going to be a 2-die solution. There's X870, B850, and B840. Now, the important thing to remember here for chipsets is that the chipset drives a lot of the I/O on the board, but the CPU also has its own lanes. So the CPU has CPU lanes, other types of I/O lanes that are assigned to various devices on a motherboard, then the chipset brings extras. Additionally, if a motherboard vendor wants to, they could add their own third-party solutions to the board, additional chips, to bring more I/O. So sometimes you'll see this with things like Quantia, 10 gigabit Ethernet, stuff like that. So 2 things to pay attention to. One's gonna be the CPU, one's the chipset. And then as far as the new boards, we're not getting any for launch. So we don't know when exactly they're gonna start being available, but we're gonna be using X670E for our reviews on July, well, towards the end of the month. And otherwise, this table simplifies everything. AMD's X870E and X870 chipsets will both run PCIe Gen 5 graphics and NVMe. That is a hard requirement, as we understand it, that motherboard vendors will have to follow. Both will also support USB 4. That is another hard requirement. CPU and memory overclocking are supported, and they run PCIe Gen 5 by 16, one of those for graphics, or they can run 2 8-lane configurations. AMD's X870E will use 2 chipset dies, and it keeps the dual chipset silicon layout of X670E. The E stands for extreme. The X probably also stands for extreme. Anyway, everything else uses a single chipset if it doesn't have an E at the end. This allows one of the chipset dies to be closer to the PCIe slots. This can be useful in trace routing. It also just expands the general purpose PCIe lane count. B850 drops to Gen 4 on the hard requirements for graphics, but can use Gen 5. That's optional. It also drops to USB 3.2 from USB 4, so that reduces down to a 20 gigabit per second requirement from AMD. And then B840 is effectively an A-series chipset previously, and it's just rebranded to either trick consumers intentionally or to just cause unnecessary confusion and havoc in the market. This is a low-end chipset. It cuts off at PCIe Gen 3. It runs USB 3.2 10 gigabit per second, so a huge drop there, and it removes CPU OC support. It also only has 1x16 graphics slot. So again, as the primer for those of you who are newer to this, if you don't know how it works, basically the PCIe slots on the motherboard, things like SATA, Ethernet, any of the additional I/O NVMe slots, i.e. M.2, all that stuff, the board vendors can pick and choose how much of each they want within the limitations of the amount of PCIe lanes they have available to them. Intel has historically called them HSIO lanes, or high-speed I/O, kind of similar in a sense, but you'll see a differing number of those I/O options based on how they want to utilize the lanes that are afforded by the chipset and the CPU combined. So that's how that works. Now, the primary difference between the X870E, X870, and the prior X670 and X670, the biggest one, we think, is USB 4 support. And then there are other meaningful changes like Availability of curve shaper, for example, we're not currently clear on if that's going to be added retroactively to all the X670E boards or not. In theory, it's possible. We're not sure if it's up to AMD via AGISA or if it's up to the board partners. So stuff like that isn't finalized yet as far as we're aware. Here's a table from AMD. This is from their website. So this shows things like general purpose PCIe lanes. Ryzen CPUs combinations with X870E will support up to 44 PCIe lanes as on this table against 36 total on X870, and both support up to 24 PCIe 5.0. X670E, the prior flagship chipset, also runs 44 PCIe lanes and 24 up to PCIe Gen 5 total. X670 non-E drops to 44 and 8 per this table. B850 and B840 are not on this table yet, but we already went over the couple things that really matter for those. So the biggest takeaway we would think is B840 is probably not where you want to be looking for the vast majority of users. And if it does sound like what you want, it's going to be ultra budget stuff. Hopefully, it better be real cheap compared to B850 because it's not a big price drop there. It's really not worth it. Think of it as an A-series chipset. But that's going to be it for this recap. There's a lot more to talk about. We will save most of it for the reviews. We have an interview with Mike Clark. It's just kind of fun talking about some of the early days of Ryzen, similar to what we did with Amit previously in the AMD lab. And that covers it for this one. Thanks for watching. As always, subscribe for more. Go to store.gamersnexus.net or patreon.com/gamersnexus to support us directly as we fund our own travel for these types of events. We don't accept travel vouchers or paid hotels or flights or anything like that. So thank you for your support, enabling us to go out and report on these things, and we'll see you all in the next video.